So physical unclonable functions or puffs are technology which is specific to silicon chips. And what we'll demonstrate in this video later on is how we've implemented this in RFIDs. And RFID being such a cost and power constrained system, this is a very cost effective way to make it more secure. So let's look at the demo of our RFIDs. So what we're going to demonstrate is our RFID chips. These are puff based RFIDs. These RFID chips that we have are standard compliant RFIDs as far as RF is concerned, and they work exactly like any other RFID except for one thing, one important thing, which is they have a puff inside these chips. The puff remains dormant, it doesn't do anything in its usual RFID operation. It's just that when you want to authenticate, the puff gets activated and you can authenticate using those silicon signatures we talked about. So let's get into the demo right away. We've created two driver's ID, and these are of course not real driver IDs. This is just for this demo. If you scan the driver's ID, what you see here is that the tag ID of the RFID chip is red, and it maps to some person called Jane Public. The other driver's ID looks very similar, so let's see how the system maps to it. And if you scan it, since it's the same tag ID, think about it as the same license number. It points to the same information inside the database. So this is same Jane Public. So which one is the real driver's ID and which one is not? With the basic RFID, you can't really say that. With this puff-based RFID, what we'll do now is enable the puff authentication. So what we've done is, for the real driver's ID, we've collected some silicon signatures. So we've collected 16 or so challenge response pairs from the real chip. So imagine that if this was DMV issuing this card, when they were collecting all this information that this driver's ID is for Jane Public and these are the various characteristics of this card, they would collect a few of these silicon signatures and store them in a database. So we've stored those challenge response pairs in a database locally on this machine, and what we're going to do is we're going to give this chip one of the challenges that we've stored and get the response, and then compare, is it close to the response that we expect from the real chip. So let's get started with this. So we keep this on the RFID reader and we enable Verayo authentication. This is the counterfeit chip or the counterfeit driver's ID card. If you look at it, these were the challenge response pairs we had collected from the original chip, and we gave one of these challenges and we got a very different response. Now let's do the same thing with the real, hopefully the real one. Let's try. We give the same challenge, and what you see here is 61 out of the 64 bits matched. As I mentioned in my previous discussion on physical unclonable functions, every time you scan the chip, the challenge response pairs are not exactly the same. You get the same challenge, you get a very similar response, but not exactly the same response. In this case, 3 bits were difference, but otherwise it matches. So that's the way to authenticate these RFID chips. You can pick any other challenge response pairs. The number of challenge response pairs you store in your database is application specific. These challenge response pairs can be extracted from the chip at any time. They could be, it has to be done in a secure location and stored in a secure database if you're using it for authentication. But this could be done on the wafer. This could be done at, say, a DMV facility if this is a driver's ID card that is being used. So that's the demonstration of these RFIDs.